So we will be doing our paper slide presentation on optimization by Sneha and Chandra. Optimization is a mathematical technique for finding a maximum or minimum value of a function of several variables subject to a set of constraints. So the steps for optimization is define the constraint of what needs to be optimized, illustrate the situation at hand, formulate both of the equations, substitute variables to create a system, derive the final equation, discover critical points where what needs to be optimized achieves its minimum or maximum value, achieve requirements of the problem, then rejoice.
So none of this should come as a surprise. At any rate, by the end of this, you'll know how to optimize, hopefully. To kick it off, define the constraint, and there's no need to exhibit any kind of restraint. The second step will entail illustrating every detail. Now come up with respective equations and work it all out till the page ends. Substitute variables, x or y. Sooner or later, this will be as easy as pie. Oh, also up here I said at any rate. That's really funny because, okay. So substitute, oh, I already did that. If you survived up until step 5, buckle up and plan to derive. The puns everywhere. Set the derivative equal to 0 to find the critical points for the problems of our superheroes. Finally, make sure you don't circle.
Number 1. Bruce Wayne feels the need to construct a rectangular parking lot for his Batmobile. He has 80 feet of fencing to work with. If the width is W, define its length and area in terms of W and find the maximum area it can enclose. So the constraint for this problem is the perimeter, which is 80 feet. What needs to be optimized is the total area enclosed by the fencing. Looking at this picture, you can tell that the length is one side and the width is the other side. You're trying to maximize the area, which is length times width. The constraint is 2L plus 2W equals 80, because that's the perimeter, and 80 is the amount of fencing you have to work with. Solving that in terms of L, you get L equals 40 minus W. Plugging that back into the area equation, you get area equals 40 minus W times W. Then distributing the W, you get 40W minus W squared. Knowing this equation is a parabola, there is only one maximum because it's facing downward. Then you take the derivative of that to get 40 minus 2W. Then you set that derivative equal to 0 to get 40 minus 2W equals 0. Then solving in terms of W, you get 20. Then at this point, you now know that W equals 20 and L equals 40 minus W. You can plug these both back into the area equation, which is 40W minus W squared, to get 40 minus 20 times 20, which equals 400 feet squared. Therefore, the maximum area enclosed will be achieved when W equals 20 and the length equals 20. Number 2. The Joker plans on turning a piece of wire into a weapon. The wire is 2 feet long and he cut it into 2 pieces to form a square from one piece and an equilateral triangle from the other. What should the length of each piece be so that the total area enclosed by both is a minimum? How about a maximum?
Alright, so we're going to do the same thing for the second problem. This one is a little more complicated. So we're going to define, first of all, to start us off. So the first thing you're going to want to define is a constraint, and the constraint here is that he only has 2 feet of wire to work with. The interesting thing about this problem is that the constraint won't necessarily be defined as an equation. When we're trying to figure out the kind of final equation, it won't be like a system. And what needs to be optimized is the total area enclosed by the triangle as well as the square. So the drawing that we need to consider is more intricate than the last problem. And here the piece of wire is drawn as a line, and it's 2 feet across in all. And one section is going to be defined as x, and the other section is going to be defined as 2 minus x. It doesn't matter which one is longer. This is just just an illustration for. It's not drawn to scale, I guess is what I'm trying to say. Not an artist. And so we're going to use the x to define the length or the perimeter of the square. So each side of the square is going to be divided by 4. The x is going to be the total perimeter. So each side is going to be x over 4. And then the area is going to equal side squared. That's the equation for the area of the square. And similarly, an equilateral triangle is going to be defined by the 2 minus x line, the 2 minus x section, and then each one is going to be divided by 3 because each side is going to be the perimeter divided by 3. So that's what is written there. And the area, as we know, is the square root of 3 over 4 times s squared. If you got really excited, you could use a lot of trig and try to figure that out, but don't get too excited because you'll waste time. So now we're going to figure out the total area that is enclosed. So I kind of put 3 and 4 together here because the first equation isn't really, the constraint isn't defined as an equation, as I said earlier. And the area is going to equal the area of the square plus the area of the triangle, which is what I kind of tried to do underlining there. So the area is going to be x over 4 squared, and then plus root 3 over 4 times each side squared, which is 1/3 times 2 minus x squared. And then you get down finally x squared over 16 plus root 3 over 36 times 2 minus x squared. And then once you have that, you can use chain rule and product rule. Just kidding. You can just use chain rule to figure out the derivative. The area prime equals x over 8 plus root 3 over 36 times 2 minus x times -1. This happens when you pull down the 2 and you take the derivative of what's inside the parentheses. And the final I guess, most simplified version of the derivative is area prime. The area prime equals x over 8 plus root 3 over 36 times -2 times 2 minus x. And once you set this equal to 0, you have to simplify it a little bit, and then once you set it equal to 0, you'll get that x is equal to root 3 over 9 divided by 1/8 plus root 3 over 18, and that's about 0.8699. And since we're in AB, they do want you to round to 0.870, despite how excited you might get about being accurate. And then we also have to fulfill the requirements of the problem. So we have to figure out where the minimum and maximum points are going to occur. So if we take that x value and plug it into the area function, you're going to get up an approximation of about 0.109. And I mean, first what you have to consider is the range that you're given. So it's from 0 to x to 2, and then do it this way. The area of 0 is going to be 0.192, and then the area of when x equals 0.870 is going to be 0.109, and the area when x is 2 is going to be 0.25. And here 0.25 is the greatest and 0.109 is the least, so therefore the minimum value will be achieved when one strand is about 0.870 feet and the other is about 1.13 feet. You have to define the, you could also, and the minimum value would end up being 0.109, but that's not what the question asked. You could put that down, I guess. The maximum value will be achieved also when all 2 feet of the wire are bent to create a single square, which is what we did. If you plug it back into the original equation, you'll see that none of the wire is used for the triangle. Awesome. The great Clark Kent needs to design a poster for the Daily Planet. He plans to work with a piece of paper that will have a total area of 200 inches squared. The poster will have 1-inch margins on either side, a 2-inch margin on the top, as well as a 1.5-inch margin on the bottom. What dimensions will give the largest printed area? Okay, so the constraint here, which we have to define, is going to be the overall area of the poster, which is supposed to be 200 inches squared. And Clark, what he needs to do is he needs to optimize the printed area. Sorry for my cameramanship. And so after we've defined the criteria of the problem, we're going to need to illustrate. So here Here is the size of the paper. It's going to be width times height, or you could do length times width, whatever you feel like. And so there's going to be a 2-inch margin on the top, a 1-inch margin on the side for each side, and then 1.5-inch margin on the bottom, right? So the area that's going to be printed is going to have to be W minus 2 for 1 plus 1, and then H minus 3.5 for 1.5 plus 2. So now you have what you need to maximize, which is the area of the printed area. This one is kind of different because both what you have to maximize and the constraint are going to be area equations. So the area is going to be W minus 2 times H minus 3.5. That's what you need to maximize. And then the constraint is going to be the entire area of the paper. So that's going to be area equals width times height, and the area given is 200. So it's 200 equals the width times height. And then the height equals 200 over W, which you're going to plug in over there. And then the equation for your printed area is going to end up being area equals, when you plug everything in, the final one is going to be 207 minus 3.5 W minus 400 over W. And then once you derive, you're going to get negative 3.5 plus 400 over W squared, because you bring down the negative, and you know the rules, hopefully. And so once you do that, you have to set the first derivative equal to 0 to solve for the critical points. You solve for the numerator, and then you solve for the denominator. Since the denominator equals 0 in our case, it's not going to work out because you can't physically have, I mean, I guess you could have no paper, but that defeats the purpose of the problem. So the numerator is going to be 400 minus 3.5 W squared, and once you set that equal to 0, you're going to get W equals plus or minus 10.690. But again, we have to focus on the restraints of the constraints of the problem and the range we can have, which can't be negative. We're not going to have negative paper unless you owe people paper, but that's not the point. Okay. Now we're going to have to satisfy the requirements of the problem, and then we need to figure out what the width is and what the height is, and we know now that the width is going to be 10.690 inches, and the height is going to be 18.708 inches. You could also figure out the area of the printed region, but on your own time, but don't do it if you don't need to. And as such, the maximum printed area will be achieved when W is about 10.690 inches and H is about 18.708 inches, and remember to do it to 3 decimal places for Calc AB.